Okay, so 10.3 is taking a look at another conic section. This time it is the ellipses. The ellipses are the ones that look like smushed circles. Okay, so with a circle, once you've decided on the center, the direction both horizontally and vertically to get out to the circle is all the same because that's the radius. But with an ellipse, the distance one direction is going to be different than the distance the other direction. Okay, and so that's part of what we have to figure out is what are those distances so that we know just sort of how much it's getting smushed, how skinny it's going to be, how wide it's going to be, and so on. So again, we'll start with definition. Whoops, there we go. So the definition of an ellipse says it is the set of all points x, y in a plane, the sum of whose distances from two distinct fixed points called foci is constant. Okay, so the first thing to point out here is that with an ellipse, there are two focus points. With a parabola, we only had one. With an ellipse, we have two, and the plural of focus is foci. So FOCI is just the plural of it, meaning that we have two of them there. So what this is saying is, in order to get an ellipse, for any points that you would have out here, in all cases, the distance from one focus to that point plus the distance from the other focus to that point, that sum has to stay the same all the way around. Okay? A very common way to demonstrate this is to take a string and tie it between two tacks like this. So the tacks are going to represent the foci, those two fixed points. This string represents the fact that the sum is going to stay constant, because this distance of string is the same no matter where I go with it. Okay, so if I take this marker and I stretch it out, I've just taken that distance and divided it up into this distance and this distance, but the two together still make the distance I started with. And now if I start drawing using that string as my guide, I get about that much for the top half, and then I got to switch over to the other side. And then I can continue on the bottom half, and the result is my ellipse.
So circles are ellipses?
Circles could be considered special kinds of ellipses, but we don't usually talk about foci in a circle. We just talk about the radius because it's all the same distance from a center.
A circle could only be considered an ellipse if the two foci were on the same point, right?
Possibly. Don't usually talk about circles in terms of foci, so I would have to think about that and look it up. Okay, so that's the idea. Now, because of the placement of my foci, my ellipse is not particularly squished. Okay, so the foci are going to determine just how flat or how wide the ellipse is going to end up being. But you can still tell the distance this way is a bit longer than the distance this way. So this is an ellipse, and so we have to be able to figure out what those distances are when we're actually being asked to graph it. We're not usually going to stick tacks into our notebook and try to graph our ellipses that way. Because in all actuality, when we get an equation, the foci is probably one of the last things we actually find. Okay? But in terms of the definition, this is a great demonstration of what the definition means. Okay? In addition to that, we've got the key characteristics for ellipses. And ellipses have a bunch. So I'm going to kind of talk through this and then I'll give you a second to get the rest of it written down. So, the line that goes through the foci is called the major axis. And the major axis is going to intersect the ellipse at points that we call vertices. Okay, so in this case, if you imagine that the foci are here and here somewhere, then this line through those foci and out here to where it meets the ellipse there and meets the ellipse over here, that is called the major axis, and where that major axis intersects is called the vertices. So not only are there two foci, there are also two vertices in an ellipse. The midpoint of that major axis, because the major axis is considered to just be from vertex to vertex. So the midpoint of that is where we would have our center. And then if we take another chord through the center, perpendicular to the major axis, we get what's called the minor axis. And where the minor axis intersects with the ellipse, we get points that are called co-vertices. Okay? And so when we get an equation, we need to figure out where the center is, where the vertices are, and where the co-vertices are, along with where the foci are going to be. Those are the four main things we're going to have to find each time. The center, the vertices, the co-vertices, and then the foci. Okay, so I'll give you a second to write down how much of that you want. And it's not showing it to you here, but the foci would be along this major axis as well. So they'd be in here somewhere. Okay, so the vertices and the foci are along the major axis, and then the minor axis is perpendicular to that through the center. Vertices are at the ends of the major axis. Co-vertices are at the ends of the minor axis. Okay? All right, so now that I've given you a little bit about the definition, you can tell me a little bit about what you found when you were playing around with ellipses on the calculator activity. So what did you find out about ellipses on the calculator activity?
That H shifts the ellipse horizontally and K does so vertically.
Okay, so H and K are still doing the same thing H and K normally do. H shifts things horizontally, K shifts things vertically, and if I give you the ordered pair point HK, then I'm giving you what?
The locate.
Center.
Center. Yep. So HK is still going to be the center, which is another one of those key anchor points, right? We've got the center on a circle, we've got the vertex on a parabola, on an ellipse, it's the center again. That's the point that if you know where that is, the rest of it falls in place around it. Okay, what else?
A and B change the width and height of the ellipses.
Okay, and where are A and B found in the equation?
The x-coordinate of the foci.
That's in the equation.
Oh, in the equation, it's underneath.
It's
the denominator.
denominators. Okay. So the A and the B values, when you were messing with those and changing those around, what that changed was the denominators that you had. And as you changed them, it changed that distance away that you were from the center. Okay? One way or the other, depending on which one you were playing with. What had to be true, or what was the difference between when your ellipse was longer horizontally or when it was longer vertically? What was the difference in the equation between those two situations?
If it's like longer this way, horizontally, then A is larger than B. And if it's longer this way, vertically, then A is less than B.
Okay, and with the way that it was set up on the calculator, that's the way it looked. Now we're going to revise that just a little bit in our explanation today. But on the calculator, the A squared was underneath x minus h squared. The B squared was underneath the y minus k squared. So when it was the number underneath x squared that was bigger, then it was longer horizontally. When it was the number underneath the y squared that was bigger, then it was longer vertically. Okay? Anything else that you noticed?
If A is equal to B, then it's a circle.
Okay? Yep, that's true. You get A and B equal, they're circles. Anything else? Do you notice anything else interesting about the equation itself?
It looks very similar to the circle equation.
Parts of it does, because you get that x minus h quantity squared, you get that y minus k quantity squared. That part is like a circle. But then what's very different about it compared to a circle?
It's over, the x portion is over A and y portion is over B.
Okay, so we have that set up within fractions. So we have denominators underneath each one. And then what else? What was it equal to? 1 every time. That didn't change. With circles, we had that all set up equal to r squared. So the r could be different from circle to circle. But with an ellipse, we are always setting up our standard form equation so that it's equal to 1. Okay? All right, so again, there are two different possibilities of what our ellipse could look like based on whether the major axis is horizontal or vertical. So it's the major axis that's going to determine how we talk about the ellipse. A horizontal ellipse has a horizontal major axis. A vertical ellipse is going to have a vertical major axis. Okay? And we've got these, excuse me, these fractions that we were talking about with the quantity squared over a denominator, quantity squared here over a denominator. We are always adding these two fractions together, and we are always making it equal to 1. But now, instead of thinking about it in terms of A is bigger or B is bigger, we need to think about it in terms of A is always the bigger number. A is always bigger than B, and they both always have to be positive. Okay? So in the case of a horizontal ellipse, the A squared, the bigger denominator, is going to be the one that's under the x squared. If I'm talking about a vertical major axis, then the a squared, the bigger denominator, will be under the y squared. So our x minus h squared and our y minus k squared pretty much just stay put. And what changes back and forth is which one of these is going to be considered a squared and which one's going to be considered b squared. And it's all about which one is bigger. The bigger denominator is the a squared. And where that denominator is determines if it's horizontal or vertical. So if we're under y-axis is this way, right? So if the bigger one is under y, then we're talking vertical.
Wait, so
If it's under x-axis is this way. So if your bigger number is under the x squared, then you're talking horizontal.
So if the bigger longer is under the x squared, that means that it's going to be wider than it is
Yep.
long. But shouldn't, like, if there's a bigger denominator, shouldn't that make x like the smaller, or that value?
It
smaller?
makes the entire fraction smaller,
Okay.
but we're just focusing in on the denominators themselves.
Okay.
Okay? All right, so how do we use the equation then to come up with these key characteristics so that we can graph? Well, the nice thing is the center is still at HK. That doesn't change. If there's no H and K, then we are assuming the center's at the origin, 0, 0. The vertices are out here on a horizontal, right? Our major axis is going to be horizontal. The vertices are out here where that major axis intersects with the ellipse. To find those vertices, the vertices are always a units from the center. So from here to here is a units. And the a units comes from the square root of the biggest denominator. Okay? The total distance of our major axis is then 2a units. From vertex to vertex, that's what's labeled down here, is the 2a units. But a actually represents center to vertex. So if I have a center point at HK, bless you, and I'm trying to come up with the ordered pair for that point right there, which coordinate has to change, the x or the y?
The
X.
The x. Y is going to stay the same, x is what's going to be different. So for my ordered pairs then, for the vertices, it's h that I'm going to add or subtract a to get those other points. K is going to stay the same. So if I add a units to my h value, I'll get this vertex. If I subtract a units from this h value, then I'll get that vertex.
Yeah, that's good.
Okay? That make sense? For the co-vertices, the co-vertices then are going to be b units from the center. So from this center point up to here is b units. That's where one co-vertex will be. The other co-vertex is going to be down there. So if that's the case, if I'm starting here at HK for center, what has to change to get that point?
Okay.
The y value, right? The k. So this time the h stays the same, and my b will get added or subtracted to the k value. So adding b is going to put me up there to the top covertex. Subtracting b will put me down there to the bottom covertex. Okay? And then last but not least, we've got the foci. The foci are going to be C units from the center. Whoa, that is nasty. Stop. Right. Units from center. But the question is, where the heck does C come from? I got a squared, I got b squared. Where'd C come from?
Midpoint between the center and the vertices.
Not necessarily the midpoint. Nope. Because the foci can be a lot of different places with the same A, the same center, and it can affect how wide or how skinny my ellipse is going to be. So, C squared has its own little equation when we're dealing with ellipses.
It's gonna be x.
C squared comes from taking A squared minus B squared. Now, why minus? Because C has got to be a point somewhere in between the center and the vertex, right?
If it was a plus b, it'd be greater than a and b, and it'd be outside the
Exactly.
ellipse.
So we know the distance from center to vertex is A. I need my distance from center to foci to be shorter than that, right? Because the foci's got to stay inside the ellipse. And so I take the a squared, but I subtract the b squared from it so that I end up with a c value that's smaller than what a was. So that that distance to the focus is smaller than the distance to the vertexes. Okay? So that's sort of the mathematical reason. What I usually remember is that it's just the opposite sign of what that is. Because what's going to happen is, next lesson on Wednesday, we're going to be looking at our fourth conic section, which is the hyperbolas. And what you're going to find, and what you maybe already saw when you did the calculator activity, is that the equation for a hyperbola looks an awful lot like this. The only real difference is that's minus.
Oh boy.
Well, guess what? If that goes minus, that goes plus. So the hyperbola also has a c squared equation to go with it, but in that case, we need the distance to be farther than what the vertex is, and so you do a squared plus b squared to get there. Now, the details of that will be worked out on Wednesday. But when we're all said and done, and we've looked at all of the conics, one of the things you have to be able to do is to pick out an equation and go, I know which conic section this is for. You have to be able to kind of keep it all straight in your head. So for me, the easiest way to keep these straight anyway is just to remember that what goes here is opposite of what goes there. So with an ellipse, I'm adding here, which means I have to subtract there. With an hyperbola, we're going to see that if I'm subtracting there, then I got to add there. But the reason for it is what we were just talking about, because I have to take the a squared and subtract the b squared to get a smaller distance than what a was. Okay, so this is how we find C, and then once we find C, is it going to affect the H or the K?
H.
Back to H again, because we're back to being on the major axis for those points. So this is going to be back to H plus or minus C, and then the K, and that's how you get the actual ordered pairs for your foci. Okay, now again, the general of all of this can be a bit overwhelming. You can kind of look at that and go, yeah, I don't know.
Yeah.
Once we actually start doing this, though, it's really pretty easy. Like when you actually put numbers in place and we're dealing with actual equations, it's actually fairly easy. You have to identify A, which is the square root of the biggest denominator. You have to identify B, which is the square root of the smaller denominator. Those two tell you how far to go from the center to get to your vertices and your covertices. And then, because it's already a squared and b squared, c squared really is just the difference of those denominators. Right? The denominators already were squared. So it's actually fairly easy to find c as well, and that will tell you where to put the foci. And just remember, foci and vertices both have to be on the major axis. Okay? Alright, so let's take a look at vertical. Vertical is pretty much going to work the same way. It's just a difference in which direction we're going to go. So the center still starts at HK. But now to get to the vertices, since this is a vertical major axis, the vertices are now top and bottom. Because I have to go the A units along the vertical axis to get to them. So if that's the case, from HK, which one gets affected in order to get to that vertex point? K. So H and then K plus or minus the A value. So it's still about the distance from center to vertex being A units. It's just that that move vertically is going to affect my K value, not my H value this time. So what do you suppose the ordered pairs for the co-vertices are going to be? Here and here.
H plus minus B.
Right. So if A is going to affect K, then that means B has to affect H. And then where are the foci going to be? On the vertical or the horizontal axis? Vertical, because remember, that's the major axis. Right? So what's my ordered pairs for the foci going to be?
H, comma, K plus minus C.
And C is still
A
C
squared.
squared equals A squared minus B squared. That doesn't change based on horizontal or vertical. That is true no matter what for an ellipse. Okay, so this distance right here represents C. This distance right here represents A. And this distance right there is B. Okay? Questions?
Not as bad as it originally seemed. Just ugly.
Alright, so let's try it with some numbers. I want you to try this first. Graph it. Identify the key characteristics, which are center, vertices, co-vertices, and foci. Those four. See how far you can get, and then we'll talk about it together and answer any questions you might have. Try it on your own first. That sounds really promising. How you doing?
Good.
Actually, I'm
That's okay.
pretty
That's
bad. Are there any square root simplifications we have to do?
What's the bottom?
I mean, so square root of 7.
That's square root of 7
How do you add that?
too. You just write plus square root of 7.
How do you graph it?
Use a calculator.
Okay, so I'm good. I've been good for a while. I was just confused.
You have to graph it using
Oh, wait. No, I just got that wrong.
Okay. I think you're on the right track.
No, it would be squares.
25 minutes.
Yeah. So for me, it's midnight tomorrow.
All right. For those of you a little stuck, let's go through this. So, which one's going to be a squared?
16.
The 16. So that means a is going to be 4. And b then needs to be 3. Okay? So this one's bigger. That has to be a squared. This one's smaller. That's got to be b squared. Okay? So based on that, is this going to be a horizontal ellipse or a vertical ellipse?
Vertical.
Vertical. Because the bigger number the a squared ended up under the y variable. So that means we're going to have a vertical ellipse. Okay? So where's my center going to be?
What, 4, -2.
At 4, -2.
Yep.
So 4, -2 is going to be right about there. And then my a value tells me how far to go from center to vertices. Vertices have to be on the major axis, and the major axis is vertical. So that means I have to go 4 up and 4 down. Those are the vertices. This is my center. Okay? The B then tells me how far to go from my center to the co-vertices, which are going to go on the minor axis, perpendicular to the major axis. So they're going to go left-right. So 3 to the right, co-vertex. 3 to the left, co-vertex. Okay? Everybody get that far? Because that's the easy part. So hopefully everybody's got that. Okay, so really the trickiest part about that is making sure you pick the correct number to use as your a squared and paying attention to which variable it's under so you know if you're talking about horizontal or vertical. Okay? Now at this point you actually have enough to graph it. You have your vertices and your co-vertices. You can draw your ellipse through those points, and again, no judgments because obviously I don't do very well. Okay? But I'm not, again, concerned about how perfect your ellipse is. I'm concerned about the points you're trying to get it through. Okay? As far as identifying my vertices and co-vertices, where are my vertices now?
4, 2,
4, 2,
and 4, -6.
and 4, -6. So when you're talking about actual numbers, it's a lot easier to come up with those ordered pairs because you just look at your graph and you figure out what your ordered pairs are. But if you look at it based on what we talked about generally, this is that -2 plus 4 plus the a, and this is that -2 minus the 4 minus the a. So it matches up, but you don't necessarily have to do it with that plus or minus a. You just look and go, oh, I went to here and I went to there, and those are the ordered pairs, and boom, write them down. Same thing with co-vertices.
The coverts.
Where are those ordered pairs now?
1, -2. 7.
And so again, technically we were taking our h value, adding 3 to it to get 7, subtracting 3 from it to get the 1, and the k stayed the same. But it's probably easiest to just look at your graph and go, yeah, that one's 1, -2, and that one's 7, -2. Now, the foci are the tricky ones for a couple of reasons. One is because they're easy to forget. Because once you have A and B, which gives you your vertices and your co-vertices, and you can draw your ellipse, it's easy to think, well, I'm done now, and not actually identify those foci. But remember, we wouldn't even have an ellipse if it weren't for those foci. So you've got to be able to place them and identify them, and that's part of what you'll be expected to do, so don't forget them. Okay? So for the foci, I have to find C. C squared is going to equal what?
60 minus 9.
Which is going to be
7.
7, so C has to equal
Square root
So
of 7.
Now, is my C value going to affect the H of my center or the K of my center?
K.
It's not a yes or no question. It's an either or question. Should it be affecting the H of my center point or the K of my center point to get to my foci?
K.
The K, because again, vertical, up, down, major axis, foci have to be on the major axis. So, I take my center point, H is going to stay the same, if my everything would work. Again. 4 is going to stay the same, and then because this is a root, it's going to look more like that general that we just talked about a minute ago. I'm going to take that -2, and then I'm going to add or subtract the square root of 7 from it. That's how I'm going to write my ordered pair. But then when it comes to graphing, I need to know about what square root of 7 is. Now, most of this is going to be no calculator when you get to a quiz or a test, so I don't need you to be exact about this. I just need you to be in between the correct integers. So the square root of 7 is going to be in between what two integers?
2 and 3.
2 and 3. So I'm going to go, I'm going to make this a little less thick so it's not quite so messy in here. I'm going to go between 2 and 3 units up and put it in between there. I'm going to go between 2 and 3 units down, put it in between there, and that is as good as it's got to get.
Good, gotta get.
Label it F, label it F. There's your foci. So I don't need you to get real precise as far as what the decimal part is. I just need you to put your point in between the right two grid lines. And as long as you do that, you're fine. Okay, so that's what our final answer should look like. This should be our graph with our center, our vertices, our co-vertices, and our foci all labeled. And then those are all the ordered pairs that relate to them. Does that help those of you who got a little stuck? Does that make a little more sense now that you've seen it? Okay. All right, so as we've seen in, with parabolas, first we want to be able to graph it. Second, we want to be able to go the other way. If I tell you a little bit about the ellipse, you want to be able to come up with the equation for it. So I'm telling you here that we have an ellipse that has foci of 2, 0, and 2, 6, and that the major axis has a length of 8. So what should we do first?
You can use the major axis to find A.
Even
Because-
before that? Yeah. Do a quick sketch. Don't try to work this all out in your head. Do a quick sketch. See what's going on. See which way these foci are going to be telling us our major axis should even go. And again, these don't have to be works of art. Okay, but a quick little sketch. 2, 0, 1, 2, that's going to be right there. 2, 6, 1, 2, 3, 4, 5, 6, that's going to be about right there. Two things I can tell really quickly from this. One, direction. My major axis is vertical now. What's the other thing I can tell really quickly?
The center.
Center, right? This is 6 units. Center is going to go halfway in between. Boom. There's my center. Which is now the point what? 2, 3. There's H and K. Okay. Now I can use the length of my major axis to figure out where my vertices would be. So what's my A value? 4, because if the major axis in total has a length of 8, remember that's 2a. So my a is going to be half of that. That means I'm 4 units away. So these were the foci. Now I have to go 4 units away from my center to get to the vertices. So one more that way, one more that way. Which means A is going to be 4. Can I tell B at this point? Just by looking at what I have? No. So how am I going to figure out the B?
Plug it into the C squared equation.
Do I know C?
You do, because you have the foci.
Yeah.
Take the center.
So remember, C is just the distance to the focus. So I do have the C value, even though I don't have B. And that's going to help me to figure out what B is. Because now I can go back to that C squared equals A squared minus B squared formula, plug in the A and the C, solve for B. Excuse me. So, if C squared equals A squared minus B squared, this is going to be 9. This is going to be 16. So what's B squared going to have to equal? 7. And here's the nice part. That's really as far as I have to go, because what do I actually need in the equation?
B squared.
B squared. So I don't actually have to go the extra step to get B by itself, because I'm just going to re-square it anyway. Okay? So now for the equation, x minus what?
2.
2 squared. I'm going to hold off for the denominator just a second. Y minus 3 squared all has to equal 1. Now, what should a squared be?
16.
16. And which denominator should I put it in?
Y.
The y squared, because this is a vertical. So the 16 will go here, which means what's going to go here?
7.
The 7. There's your equation.
Noise.
Okay? Questions on how we came up with that? How we put those pieces together? Okay? Let's get to the fun stuff. This is funner. More funner.
More fun.
So this is what a general equation for an ellipse would look like.
Ah.
But if you look at that, can you tell what A is? Not really. Can you tell what B is? No. Can you tell what C is? Can you tell where the center is? Not really. No. So, although this is an equation that represents an ellipse, in terms of graphing or knowing anything about the ellipse, this is not real helpful. So we need to be able to take this general equation again and rewrite it as a standard equation, so then I can tell all of the things I need to tell to sketch the graph. Okay? So if you remember with parabolas, we said that we were going to keep whatever variable was being squared, because only one would be squared. We were going to keep that on one side with any other terms that had that variable in it, and then move everything else on the other side. Right? And then we would use that squared variable and the linear variable that went with it and complete the square. Okay? Well, now both variables are squared. Both x and y are squared. So we're actually going to leave all of the x and y terms on the same side. The only term we're going to kick out is the constant. We're going to move it to the other side. But then we're going to regroup things so that x's are all together and y's are all together. Okay? And so it's going to look something like this. I'm going to try to do this in different colors to help you kind of visualize what's going on. So x's I'm going to make blue. So that's x squared plus 6x. The y's, let's make those purple. So we'll put those together. 4y squared minus 8y. And then the constant we're going to kick over to the other side. Okay? Now if you think about where we're going, if you think about the standard form and what it needs to look like, in the standard form we have both an x quantity squared and a y quantity squared. And so what we're going to need to do is complete the square for the x's and complete the square for the y's.
Sad.
I don't know why my pen's being so weird today. There we go. Okay.
Wow.
So, for the x's, what do I need to add to x squared plus 6x to complete my perfect square trinomial?
9.
A 9. Half of 6 squared is going to be 9. Okay? Now, what about with the y's? What am I going to have to do to complete the square for that?
You factor out 4.
We got to factor the 4 out first. And remember, we have to factor it out of both y terms. Because in order to take that half of the linear coefficient and square it trick, we have to have a leading coefficient of 1.
Okay.
So we're going to take the 4 out, which means what's left here in parentheses is y squared minus 2y. And then what do I need to complete that perfect square trinomial? A plus 1, because now half of that squared will be plus 1. Now, remember, whatever I do on the left, I got to do on the right. So I started out with a negative 9. But what did I add to complete the x's?
9.
A 9. So I'm going to need to add a 9 over here. Do it in blue, because that's where that came from. And then what did I add on the left side for the y's?
1.
4. 4. Because everything in this parentheses has a multiplier out here. So even though it's a 1 that completes the square, I actually added a 4 to it. Because that 1 gets multiplied by that 4. And so I need to do that over on this side as well.
Oh.
Okay?
Yeah.
Alright, so now I need to rewrite these as a quantity squared plus a quantity squared equal to some value. So how am I going to rewrite x squared plus 6x plus 9 into a quantity squared? X plus 3. Here, I keep the 4 out in front, and then y squared minus 2y plus 1 is going to be rewritten as what? Y minus 1 squared. And then over on this side, what's that going to end up being in total? A 4, because the positive 9 and negative 9 cancel out, and so we're just left with the 4. So we're getting close. We've now got those x and y quantities being squared. But now what's the other thing about the ellipse standard equation that has to be true? It's got to equal 1. So how am I going to make that happen? Divide everything by 4. So this gets divided by 4, this gets divided by 4, this gets divided by 4. So my standard form equation now is that x plus 3 squared is going to be over 4. what happens here?
Y minus 1 squared over 1.
Over 1, because the 4's are going to cancel. Yep. So this is going to be y minus 1 squared over 1, and then 4 over 4 is equal to 1. Okay, so now I should be able to identify a and b. Which one's going to be a squared? The 4, so a's got to be 2. Which one's going to be b squared?
1.
The 1, so b's got to be
1.
1. Just need to make that bigger again so I can actually put this stuff in here. So center is at -3, 1. Right about there. And now I'm going to go A for 2, B for 1. Is this a horizontal or a vertical ellipse? Horizontal, because my a squared is under x this time. So that means 2 to the right, 2 to the left, and then 1 up and 1 down for b. So it's kind of a tiny little ellipse. It looks something like that. Okay? And then where would the foci be? So c squared is going to equal what?
4 minus 1. So root 3.
So c has to equal,
Root 3.
Oh, yeah.
and root 3 is between what two integers? 1 and 2. So I'm going to go a little bit more than 1 this direction and a little bit more than 1 that direction, and that's where the foci are. Okay, and then we can identify all those points. We know center is at -3, 1. Where are the vertices? -1, 1. And what's the other one?
-5, 1.
Co-vertices? Foci?
-3 minus root 3. Okay, that was it. 1.
There you go. Okay, so anytime you're getting a C value that's a root, which is going to be most of the time, all you need to do is figure out, does that affect H or K, based on whether it's horizontal or vertical, and then just write it as the H that I had plus or minus whatever my C is. Okay? Or the K that I had plus or minus whatever my C was if we're going vertically. Everything else should usually work out pretty nice. But if it doesn't, if for some reason, you know what A is, which is a nice number, and you know what C is, which is a nice number, which gives you kind of an ugly B value, then it's the co-vertices that you'll just do the plus or minus whatever that root is and do it for that instead. But usually it's the foci that it happens to. Okay? All right. Last question. A little bit of application here. So it says the moon travels about Earth in an elliptical orbit with Earth at one focus. So Earth is actually not the center of the orbit. Okay, it's at a focus. The major and minor axes of the orbit have lengths of 768,800 kilometers and 767,640 kilometers respectively. Find the greatest and least distances from Earth's center to the moon's center, and they just happen to have specific names, which are the apogee and the perigee. And I don't honestly know if it's G or G, but you get the idea. So the real question here is, where would the moon be in the orbit for it to be the shortest distance from Earth and the longest distance from Earth?
So I just find the vertices.
So that's the first thing you need to realize, is what we're really asking for is, how far away are those 2 points from Earth? Because its shortest distance is going to be here when it's on the major axis. Its longest distance is going to be here when it's on the major axis, and the endpoints of the major axis are the vertices. Any other place along the orbit, we're going to be a little shorter than this, but probably longer than that.
You can find the center by getting half of the major axis, right?
Okay, do I actually need the center? Half of the major axis actually gives me what?
The
Since
center.
we're looking from
Well, I was thinking about finding the distance from the center to Earth. I don't know if that's what we have to do.
Okay, but if you go back to what you said a second ago though. If we take half of the major axis, what have we just found? A. So it's not so much about the center in terms of the ordered pair, the point. It's more about the distance. Okay? And so the distance from center to either one of the vertices is going to be A. Now, what is the distance from Earth to the center going to be? C.
And we know B. Yeah, we do. So that's easy.
solve for B.
And we can figure out B by doing what?
Half of
Minus.
the minor.
Okay, so what is half of major?
6. So 68.
Say again?
Oh.
You guys have the calculators, push the buttons.
It's gonna be like
I love how you always look at me like I'm gonna...
384,000.
Hey, I still got it right.
How much?
384,000.
384.
I just said
Exactly.
This is loading.
384,000.
400.
Because it can't just be 380.
Oh, I put the wrong number in, so 400 in. Is actually part of that number. I thought it was implied.
368800. 384400. Yes. Okay. How about half of minor?
383 820.
So I did like it too. Human calculator.
Okay. So how are we going to find C?
C squared.
A
A
squared.
Whatever. Oh, okay.
Sorry, I can't know that.
Easy head.
So what is the different, the maximum distance from the Earth's apogee to the moon's apogee?
So tell me what C squared equals first.
They're curious.
Between the Earth and the moon.
I'm computed. It's
It's computer drawing.
about.
Okay, C squared equals 4
4,
4
4,
5
5,
5
5,
6 7 6 0
0, 0.
That's right. Absolutely.
5, 6,
That's
7,
45
Yeah.
Okay. So that means C has to equal what?
That
Yeah,
to the power
you've
of
got the
1.
buttons.
21108.47.
21108. So yeah, we'll just leave it. I mean, we're talking this big of numbers. Another half kilometer is just not going to make that much difference. Okay. All right, so have I answered my question yet?
No.
Nope.
No, so what do I have to do to answer my question?
Well, I had to subtract C from
A.
A.
A. So if I take A minus C, what does that give me?
Oh, actually.
Such big numbers.
363,292.
200 what? 92. Okay. So is that the longest or the shortest?
That's the longest.
Yes.
Yes.
No, shortest.
The shortest. Because this is A, and this right here is C. Okay, so taking A minus that C gives us our shortest distance. What about the longest? So A plus C is going to give us what?
405,508.
So that's this A value plus that little extra C to get to Earth. Okay. So again, being able to work with a problem like this comes from understanding what ellipses are all about, what the key characteristics of ellipses are, so that you can use those to find the pieces that you're being asked about. Okay? All right, so that's it for the lesson. And that should get you through your homework for tonight, which is posted on Canvas. But let me just talk a little bit about the rest of the week quick. So whether you're here or not here, you kind of know what to expect. So I will not be here. I think most of you know I coach softball, so I will be gone for APAC as well. So Wednesday, Thursday, and Friday, I will be gone. I know several of you will be gone. If you are here on Wednesday, we're going to tackle the last conic section, which is the hyperbola. You're going to get the information you need through a video lesson. So please bring earbuds with you. Okay? That way you can watch the video at your own pace, take your own notes as you watch, go back and rewatch sections if you need to see it one more time, but you can do that without disturbing anybody else around you. If you have questions on something, you can ask people around you, but for the most part, you should be watching and listening yourself, taking your own notes, and then when you're finished with the notes, you'll have some time that you can get started on the Canvas assignment. Okay, so that's for Wednesday. Those of you who are not here Wednesday, I hope to have that video posted sometime tonight. So if you get a chance to look at it before you go, great. If not, take a look at it when you can so that you make up that lesson. On Friday is scheduled to be a review day. It's a chance for you to now take all of the conic sections sort of together like you would see on a quiz or a test and have to deal with them all at once. And in order to review, there's going to actually be 4 different little activities that are going to be going on, and you're going to kind of rotate through them like stations. So if you're here, you'll get the benefit of all of that. One of the stations is going to be creating a foldable. The other 3 stations are going to be working on different kinds of review problems. Okay? And you'll get more details about that on Friday. Basically, the day is set up on Canvas. And so each of the stations has a set of directions on Canvas that you just, when you get to that station, you follow those directions. It'll be pretty straightforward. If you are not here Friday, then the 3 stations that are review problems, you do as much or as little as you need to do to feel good about what you're doing. But I definitely recommend that you at least do the foldable, because I will allow you to use the foldable on some quizzes and the test. So if you don't make the foldable, you're going to be at a distinct disadvantage. The foldable is set up where it's already printed off what you get to fill in. So it shouldn't be any big mystery as to what you get to fill in on this thing. The biggest part is just going to be constructing it and then doing the fill in during your time at that station. Okay, so it's pretty straightforward, just as long as you construct it the right way so that it makes sense, and I'm trying to give you directions to guide you through that, then it's just a matter of filling in what's allowed on the foldable from the notes that we've already done. And it should be pretty direct right from your notes onto that foldable. Okay? On Tuesday then, when we all get back, there is a quiz. And yes, I am expecting all of you to be able to do that. I do not have a lesson planned for Tuesday, so that means we'll actually take the first half of the period to go through any questions you still have, and then take the quiz the second half, rather than what we usually do, which is quiz first half and then some lesson second half. We will answer questions first half. When I get back, everyone's had a chance to kind of get caught up, review, do whatever they need to. The quiz will then be the second half of that period. Okay? Any questions about that? So you're not missing any assessments. It's basically one lesson that you'll need to watch on a video, and then review time, and for those of you gone, at the very least, make sure you get the foldable made. Okay? All right, and go ahead and get packed up. Please wait for the bell.
So Miss Gordon.
Yeah.
So for softball, we were watching you guys for track. The catcher doesn't wear a mask.
No, because it's slow pitch.
But what if a foul tip goes back and hits you in the face?
They got to be heads up. But
So
yeah,
you're
there's
not allowed to wear catcher's masks, or
No.
is that?
You don't wear any equipment.